Good.
Okay, we're good. Are you okay for noise?
Yeah.
We're doing a kind of survey, trying to find somebody in climate science who started studying climate. What did you start studying? Your career?
I started with mathematics. I was a mathematician at Oxford. My PhD was in applied mathematics, fluid dynamics, that was vaguely associated with the ocean. But then as I became a postdoc, I became more interested in the climate.
Why?
Because that's where the most interesting questions were. You know, it's
For instance?
there's a lot of complexity in climate science that when you're doing kind of pure mathematical problems, you kind of average away, you kind of assume away. You know, let's assume that everything is a. Let's start with a spherical cow, right? So yeah, it's applied mathematics is very similar. But when you see real problems, and then you want to have questions that are associated with, you want to have answers that are relevant to the real world. It's not sufficient anymore to just assume that all of the complexities go away. So you have to kind of tackle all the complexities. That means that you have to be looking at real issues and including all of the little things that are only happening in the world. And that means that you're not going to have like a really easy answer, right? You're not going to be able to just write down the equation and solve it, right? So that happens. That's what you do when you're a mathematician. But when you become like a climate scientist or you're looking at something that's far more complex, then you have to accept that it is more complex, and you have to use different methods, different ways of thinking about it. But it's also much more interesting, and it's much more of interest to other people.
Still, to model climate, you need to know a lot also about biology, not only about fluid dynamics, about geology. Is there anyone in your field who can master all these kind of disciplines?
So no. I mean, there isn't one person that knows everything that's related to climate. And climate itself, as a field of study, keeps growing. It used to be, it was like the meteorologists and the oceanographers, and then the ice people, and then the land surface people, and now the glacier people, and now the vegetation people, and now the microbial biology people, and now the ecosystem people, so as a problem, it's expanded way beyond the competency of any one single person. So by its very nature, it's a collaborative work. We have to be both humble in that anybody individually doesn't know everything, but also kind of ambitious in that we need to get everybody to be on the same page. And not everybody wants to work like that, but there's enough people who want to work like that you can move forward. But it's fundamentally a collaborative effort, and that's really why it's so exciting.
Now we're proceeding chronologically. So we started with mathematics, then modeling, fluid dynamics, and then the climate, which is much more than fluid dynamics. Now we're getting to the models you've been doing. When did you start modeling? Let's say at the Goddard Center.
So I've been there about 16 years.
16 years. So what improved, and where are the knots that you still?
So when I arrived, I don't think we, as a group, we really realized what was required in order to be competitive and to be doing cutting edge science. And so, we'd done a lot of good stuff in the past, but it kind of splintered and gone different ways, and it wasn't very coherent. I got there and I wanted to do some kind of very specific things, which meant that we had to bring things together, and that became a much more coordinated effort. And so I've ended up running that effort, and so now we're much more coordinated than we were, and that's allowed us to make a lot of progress in a lot of fields where we weren't making progress.
For instance?
So in combining atmospheric chemistry and aerosols and all the different sources and all the different interactions and taking the models up to the stratosphere and beyond and improving the oceans and improving the like just kind of putting things together and looking for different ways in which all the different elements interact. The fact that the wind affects the dust, and then the dust affects the sulfates. The sulfates is affected by the chemistry, and that's affected by this, and that's so making sure that we've put in all of those kind of hooks and those connections. We're one of the groups that maybe there's one or two other groups that are on the same kind of level, but really, it's like 3-4 groups in the world that do what we do.
And you confront them. You confront the result from time to time. You check the results
all the time. All the time. So we build the models and we say, okay, well, this is our best estimate of how this process works. This is our best estimate, and then we look for the data sets that allow us to check. So is there an impact of ENSO on these things? Okay, well, we can look at all the different times there's been an El Nino and we see whether there's the same thing that we see in the model is happening in the real world. When we're looking at ozone fields in the stratosphere. So, we try and predict when the ozone hole should have happened. And, the ozone hole happened then, and yes, the chemistry that we put in produces an ozone hole at about the right time and about the right level. So there's lots and lots of things that we're doing where we've got good observational data over the modern period, where we can test that the models are doing a pretty good job. But that's not sufficient. Because we're not just trying to match what's happened already. We're trying to see whether the models have predictive power, right? Whether they can predict something that's going to happen that hasn't happened. And for that, what we're trying to predict is like decades ahead. So we can't just sit around and wait. I mean, we'll be able to check it in 30 years' time, but in the meantime, we're trying to get a better handle on it. And for that, we're looking at paleoclimate. We're looking at how things changed in the past, why they changed in the past, and whether the models can do a good job at that. Where we've got data that's not as comprehensive as the data we have in the modern period, and it's different kinds of data, right? It's ice cores, it's cave records, it's ocean sediment, but the signals are much larger, right? So what we've seen over the 20th century is small compared to what we expect to happen, and they're small.
Pardon? Because there is it's early this year.
Yeah, just random. And we're not looking just to see small things, but if you go back in the past, there are really big changes that the models should be able to predict. And we're at the point now where we're really coordinating very well with the people that are looking at that data, trying to understand that data, and matching it up to the models. And it's producing a lot of reasons to think that the models are credible.
Now, models work on, they're long-term, they work on the long term. Both in hindcasting and forecasting.
Right, but they work on the short term too, right? So every model experiment you're doing, they're working, every 30 minutes, every 20 minutes, they work all the time.
Yes, of course. But at the end, when you get to the publication and to the assessment report of the IPCC, what you have is a forecasting for the next generation. Governments, and I think even some agencies in the United States, maybe the NOAA, are working on intermediate models, 5-10 years models, aren't they? What do you think?
Okay, so the issue with short-term predictions is not that the models aren't calculating it; they're all calculated. But what happens is that the answers for the next 5 years are actually very dependent on exactly where you start. So if I start a model and I start it in the 19th century, and I just say, okay, come along, and now we're in 2010. The climate change is the same every time I do that.
Yes.
But the weather in any particular case, whether there's an El Nino event or a La Nina event, is completely random, right? So it's forgotten everything that it remembered back in 1850. So if we're now in 2010 and you say, well, what's going to happen in the next 5 years, it really matters that 2010 was a La Nina year and the oceans were in this particular state. And if we use that information, the idea is we should be able to have a better prediction for how that's going to evolve over the next few years. Because it's not until you get to like 10 or 20 years that the change in carbon dioxide is really going to make a big difference. Right? So that's ongoing. But on any kind of short-term basis, you've got lots of ups and downs, you've got lots of noise which is associated with the weather, with the ocean weather, which isn't predictable because you know what carbon dioxide is, but it might be predictable if you know exactly what the ocean is looking like. So you've got two issues there, right? One is, do we know what the ocean looks like exactly? Okay, so for now, yes, probably enough. But did we know it 10 years ago or 10 years before that? No, we didn't. So it's very hard to test these predictions. Secondly, we're not really sure how to do them, right? So there's a philosophical and a kind of practical issue that's associated with, well, how do you start that? If you just say, okay, well, let me just put in what we see right now in the ocean and then just go forward, what happens is the model just wants to go somewhere else completely, because the model has its own climate and it just wants to go to that. And so, you're not looking at how the real world will go. And you think, well, I'll just put in the differences, and then that has another problem. So technologically, there are some issues with this, and so it's not at all clear how useful these kinds of short-term predictions are going to be.
I see.
But it's definitely a worthwhile research field. But as a member of the public, I wouldn't if you're looking for operational climate forecasts in the same way that you get operational weather forecasts, you have a long time to wait.